Today we're going to prove that two counter machines are Turing equivalent. First off, what is a counter machine? Well, a counter machine is a machine with the following properties. It has an unbounded register to store a non-negative integer value. It has a state register, which stores the current instruction it is executing. And it has a finite list of sequential instructions. Common instructions include increment and decrement, which increments or decrements the register that stores the non-negative integer value. Clear, which clears the integer, or the register that's storing that integer value, or it zeroes it. Unconditional jump, which jumps to some instruction I sub k. Jump if is 0, denoted as JZ, which jumps to some instruction I sub k if the register, the given register is equal to 0. And halt, which halts the machine. So this is the visualization of the counter machine. As we see, the R sub 1, R sub 2, and R sub 3, and so on, that is your unbounded register that stores the non-negative integer value. You can pull each individual integer as shown on the screen. You have I sub k, which is your state register, it's the instruction you are currently executing. And then you have some finite list of instructions, and that is your I sub 1, I sub 2, up to I sub n. So these are the steps that we're going to follow to prove that two counter machines are Turing equivalent. We start off by showing that a Turing machine can be simulated by a two-stack PDA. And then we show that a stack can be simulated by two counter machines. And finally, we show that two counter machines can be simulated by a single counter.
All right, thank you, David. So as David mentioned, the first step in showing that two counters are Turing equivalent is showing that a Turing machine can be simulated by a two-stack PDA. So at a very high level, a Turing machine is a non-deterministic finite automata with an infinite tape. And to convert that to its two-stack PDA, we will slice the infinite tape at the head and put the first part into one stack, into the first stack, and then the second part with the head into the second stack. So now the head, so to speak, is at the top of the second stack. Next, we need to simulate movement. So to move right in the two-stack PDA, we will pop from the second stack and push to the first stack. And then for left movement, we'll pop from the first stack and push to the second stack. Now the last thing that we need to be able to simulate with the two-stack PDA is reading and writing. So reading's pretty straightforward. When you're performing a movement and you just want to read, whatever stack you're popping off of for that movement, you would just push the character that's popped off into the other stack. Now for reading, it's a slightly more complex. When you pop off the stack that's necessary for that movement, you then change the character and then push it into the other stack. And that is all that is necessary to simulate a Turing machine with a two-stack PDA.
Shown how a Turing machine can be simulated by a two-stack PDA, I'll go ahead and show how a stack can be simulated by two counters. First off, we can use a stack to represent a binary number with the topmost bit on the stack representing the least significant bit. So for example, the stack below represents the binary number 1101. Now there are numerous stack operations. First off, pushing a 0 at the top of the stack results in doubling the number. So for example, 1101, which is a 13 in decimal, gets converted to a 11010, which is a 26 in decimal. Next off, pushing a 1 at the top of the stack results in doubling the number and adding 1. So a 1101, which is 13, gets converted to a 11011, which is a 27 in decimal. And finally, popping a 0 or 1 off the top of the stack results in dividing the number by 2 with a remainder of 0 or 1, depending on whether a 0 or a 1 was popped off. So for example, 1101, which is a 13 in decimal, gets converted to a 110, which is a 6 in decimal with a remainder of 1. Now we can use two counters to simulate these stack operations, with counter 1 storing the decimal number represented by the binary number in the stack, and counter 2 initialized to 0 and being used as a scratch pad. Now to simulate the stack operations, first off, to double the value held by the first counter, we can repeatedly decrement counter 1 once and increment counter 2 twice till counter 1 reaches 0. And finally, counter 2 would ultimately store double the value of counter 1. And then to halve the value held by the first counter, we can repeatedly decrement counter 1 twice and increment counter 2 once till counter 1 reaches 0, and ultimately counter 2 would store half the value of counter 1, and then this remainder would be 0 if it was reached in an even number of steps, and the remainder would be 1 if it was reached in an odd number of steps.
Hey there, my name is Spencer Shook, and I'll be covering the last part of the proof. So the last step we need to do to prove that a Turing machine and a two-counter machine are Turing equivalent is to show that 4 counters can be simulated by 2 counters. So in this case, we're still going to use 2 counters and then show how it can simulate the 4. So counter 1 is going to hold the integer with the prime factorization of the form 2 to the a, 3 to the b, 5 to the c, 7 to the d. Now this could actually work with any set of prime numbers, but for simplicity, we use the first 4 here. So in this case, the numbers a, b, c, and d in the form represent the numbers in the 4 counters. So that means if this was a number 2 to the 1, then the rest of it, then counter A would hold the number 1 in it. And then we're still going to use counter 2 as a scratch pad. So now I'll briefly cover how this still works, that we can cover all the operations using the 4 counters simulated in 2 counters. So if we wanted to increment any one of the counters, we can multiply that number by the base b, where b is the prime number as the base for that counter. So in the first example here, increment, we have 2 to the 10, 3 to the 10, 5 to the 10, 7 to the 10, and then we want to increment the second counter, so we multiply that by 3. Then all the other powers stay the same, but the 3 has the power raised from 10 to 11. Thus, we've incremented that value in that counter from 10 to 11. Then, the same thing works with decrement, except we divide, thus reducing the value stored in that counter by 1. And then if we wanted to do a check operation, such as a conditional jump, we could divide the actual counter by the base b, check the remainder, and then add the remainder back into the actual counter to preserve the state. This would allow us to perform the conditional jump operation.
In summation, we've shown that 4 counters can be simulated by 2 counters, and that a stack can be simulated by 2 counters. We've shown that a Turing machine can be simulated by a 2-stack PDA. Therefore, we've shown that a 2-stack PDA is at least as powerful as a Turing machine. We felt that it was trivial to show that a Turing machine can simulate a 2-stack PDA, therefore we did not include it in this presentation. Considering all these different proofs, we can conclude that a Turing machine and a finite state machine with 2 counters are equivalent in power. Now to move on to some related topics. These are mostly concerned with counter machines. So the first is the decidability of checking if a language is prime with a deterministic 1 counter machine. And the second is the minimal amount of counting machines that act as a base k counters. And then finally our citation. Thank you very much.